Okay, so here's a really long and wordy example of this being applied in three dimensions. Now, if you pause the question and have a look at this, it's not actually answering anything to begin with. What we're going to do first is we're actually going to draw this situation, and then I'm going to put into place the two questions that we're going to be asking. Okay. So a vertical mast is supported at the top by two cables reaching from 2 points A and B. Okay, so let's draw that to begin with. So the vertical mast, so something like this, but drawn properly. Okay, something like this, probably. Okay, and I'd say, like, it doesn't really matter where these two masts, and these two cables sit in relation, okay, because it hasn't told us whereabouts they are, okay, but think of these as like two little cables, the two little anchor points, okay, and then this is like where this is like the mound where the pole or the mast is standing. Now, excuse me. The cable reaching point A is 36 meters long. Okay, so if we call this one point A and we call this one point B, okay, we know that the cable, so the length of the cable, so that's the red bit, is 36 meters long. Okay? And we also know that so that's this 36 meters here, and is at an angle of 48 degrees to the horizontal. So 48 degrees to the horizontal. So if I just imagine this was like a flat sort of plot of land going that way, okay, so like from here to here, like it's all flat, like, this pole, it's not like hovering in the air, like it's flat. This is just like a sort of like imagine if these cables were coming towards you and the pole sits back a bit, like it's going to look like they're they're closer to you, so it'd be flat along here. Anyway, the reason why I want to point that out is because we're looking at this angle in here, and this angle in here is 48 degrees. Okay? So that's 48 degrees to the horizontal. Now, point B is 24 meters from the base of the mast. Okay, so if I draw this triangle out, then what it's saying is that this length along here is 24 meters. Okay. So this is the situation that we've been given. Now, part A of this problem, of the actual problem, so all we've done is we've just drawn the picture. Part A has said we're going to find the height, correct, to 3 decimal places of the mast. Okay, so that is the pole. Okay. And then part B, so we'll do that in a moment, find angle to the horizontal of the cable reaching from point B to decimal places. Okay, so these are the two questions we're going to have a go at. Find height corrected 3 decimal places. So if I let's call our height a letter, and I'm going to just call it the letter X, or actually, in fact, I'm going to call it the letter H. H for height. And part B, find the angle to the horizontal of the cable reaching from point B. And so that's this angle in here. And let's mix up a bit. Let's use a different letter. Let's call this angle, call it angle beta. Okay, so that's just a Greek letter. You could call it theta or beta or alpha or gamma or whatever you want. Probably not sigma though, because it's used for a lot of things, or pi. But any Greek letter works there. So let's have a go at finding this height. Now, even though this is a situation that's in 3 dimensions, okay, we've still actually only got, like, this is still just a picture made up of two shapes. Like if we have a look here, this here is just a right angle triangle. Like this is just a triangle that we've been dealing with this moment. Okay, so let's transpose this into 2 dimensions. Okay, so, and the reason I'm picking this triangle to begin with first is because I actually know information about this triangle. So what do I know about this triangle? Well, this particular triangle, what we know, okay, we know that the angle in here is 48 degrees, okay? We know it's a right angle triangle, and we also know this length here is 36, okay? And this is our height here of our shape. So this is the height of our pole. Imagine this was the pole, okay? This is my point A, so this is the length of the cable down here. So let's do some trigonometry to find what the height of the pole is going to be. Okay. So Sokotoa. Okay, so which of the 3 trig ratios are we going to be using? So hopefully you picked it's going to be the sine ratio, because what we've got is we've got the opposite and we've got the hypotenuse. Sine uses the opposite and the hypotenuse. So write the formula out. Sine theta is equal to opposite over hypotenuse. Substitute the values that we know. So sine of 48 degrees is equal to, so the opposite we've just called h. We don't know what it is. It's just the height of this mast over 36. Now recall from the previous lessons that when we have an unknown on the top here, okay, we want to get rid of this 36. The way we're going to do that is we're going to move the 36 up to the other side, or we're going to multiply both sides by 36. And by doing that, that leaves us with 36 times sine 48, or just 36 sine 48, which is equal to h. So my h value, substituted into my calculator, we get 36 sine 48, close it off, hit equals, and we get that the height of the mast is 26, and I think it's a 2 decimal places, 3 decimal places. So the height is 26.753. So it's part A. So let's go back up to our picture. So that means that this height in here, so the height of this mast here, is actually 26. I'll put a 7 there. 26.753 meters. Now, finally, we want to find what angle beta is, okay? So just like before, we're going to transpose the other triangle this time out and work out what the angle is going to be. So this angle in here, just like we did in the previous video. So let's bring this right angle triangle down. Okay, so this is part B. So I'm bringing this right angle triangle down. It's going to come sort of out this way this time. I'm probably not out like that. Okay, I wasn't expecting that. Okay, like that. Okay, now we're trying to find what this angle in here is this time, which we've called beta. Okay, again, it doesn't matter what letter you use there. Now we know that the point B is 24 meters from the mast. So that's this length down here. And now we also know the height of the mast. So that's from the top here down to the bottom is 26.753. And that's why we had to do part A before we did part B, because we actually had to work out what the height was before we could do this angle part. Okay. Oh, excuse me. All right, so because it's a trig problem, we're going to look at Sokotoa again. And we're thinking to ourselves, well, which of the trig ratios are we going to use? So looking at this one here, we've got a opposite and we've got an adjacent this time. We don't have anything on the hypotenuse. So we're going to be using TOA or tan. It's going to be tan theta is equal to opposite on adjacent. So this is just me writing my formula out. Now we're going to substitute in what we know. Well, we don't know what the angle is, so I'm going to put my beta in there. Okay. The opposite is equal to 26.753 over 24. Okay, so beta is equal to, and this is where we do the tan inverse again, and we get 26.753 over 24. Okay, like that. And so beta is equal to, I'm going to put this in, 26.753 over 24, close it off, and we get that it's equal to about, and I think it's set to two decimal places. So we're actually going to leave this one in decimal terms. It's going to be 48.10 degrees, like that. Okay. And so that's pretty much it. Now, if me using that beta in this case confused you, just call it theta. Like, it doesn't matter what you put in that angle thing there. But this is just trig stuff that you guys have been practicing over the last days. The only thing that's different is that it's in situations where some of them are going to be in 3 dimensions, okay? Just think about the picture. Just think about where the triangles exist and how can you transpose them into 2 dimensions, okay? Most of the 3-dimensional problems with trig are just doing 2 applications. So another big one, which we won't actually do, but another big, well, not a big problem, but another problem that usually arises from 3-dimensional trigonometry, or even 3-dimensional Pythagoras really, is if you've got a box, okay? So just some random box like this. I don't know how well that's been drawn. But if you've got a box like this, and you wanted to work out what the distance from one corner to another corner was, well, what you could actually do is you can, if you know what one of the angles are, okay, you can work out what the distance, what the length along the corner is by using the 2 side lengths. Okay, but that's just another application of this. Okay, so have a go regardless and see how you go. Okay, and remember, we are here to help you, so please do ask if you do have any. So with that being said, good luck, and as I said, any issues, please do ask.